Alright, this is designer Aaron Chan with project manager Christian Ricci here for assignment 2. Now, for our Gantt chart, we have updated to reflect the new dates and deadlines for assignments, and we will make adjustments to the timeline and scope if necessary. Now, for the planning, the changes to our design between assignment 1 and now. So instead of using the Arduino Uno, we have decided to use the more compact Arduino Nano. Our focus has also shifted from a tire and wrench combination to just on the tire peripheral itself. And we have decided to use rotary encoders instead of potentiometers in order to eliminate the foreseeable need of having to figure out a way to reset the knuckles after use. Another addition that we added are magnets to the lug nuts, just for general feedback. So there's a click sound when the magnets attract to the wrench, and so there's the magnetic pull to show that the wrench is in the intended position.
And one more key point we wanted to highlight that was a major change in our development is that we're actually utilizing an actual torque wrench rather than making a controller that potentially could come with a lot of design flaws to it. And this idea was suggested by Alvaro, and we took it into consideration and realized that using an actual wrench would make our lives a lot easier and will feel more accurate to the simulation since you'll be using the tool that you would need to change your actual tires with.
We have the paper prototype. As you can see, we have our 5 lug nuts, which we're able to rotate with our torque wrench. And underneath it will be our 5 rotary motors. And if you take off the lid, you can see that we have the motors just on a platform here, which underneath you can see the space for the Arduino. And there's also going to be a part on the side, which we can use as the USB port here.
Circuitry-wise, the setup is pretty simple. Now, in Tinkercad, we have potentiometers and the Arduino Uno, but our actual project will be using a Nano as well as rotary motors. But we opted to represent it this way in the circuit diagram due to Tinkercad not having what we actually need, so we just represent it using equivalents. Now, code-wise, it's pretty simple. We simply have it so that the motors will send a signal to the Arduino when it text rotation, like so. And depending on how much they turn it, we'll have a different number. So we can pretty much get how much they rotated.
Alright, so when it comes to the bill of materials and parts list, we spent a lot of time to determine what we actually needed in order to achieve our goals. On the left-hand side, this bill of materials was created while referencing the components needed from Tinkercad, along with other general components that we needed to acquire. Mainly, we focused on determining our 3 key hardware components, which consist of an Arduino Nano, rotary encoders, and a breadboard. We also looked into things like jumper wires, magnets, and an actual torque wrench, since that will be our controller. Now, regarding the parts list from Fusion, we laid out all the 3D printed components we will need to make along with the essential hardware components. As you can see, we have 5 3D printed parts that each serve a different purpose, which I will also explain later, along with the Arduino, breadboard, and rotary encoders. Now, when it actually comes to the technical drawings, we have 5 in total, which I will have a brief overview of. So first we have the rim assembly overview, which is just an overview of the entire peripheral itself. We have a technical drawing for the shell, which is a piece that you can remove off the base of the tire. We also have the base drawing itself and how that works, and another technical drawing for the 3D printed lug nuts, which we wrap around the rotary encoders. And finally, we also have a technical drawing for an elevated platform, which is situated in the middle of the tire. Alright, so taking a deeper dive into Fusion 360, I'm going to highlight the model we created and the purpose of everything that we intend for this model to achieve. So the first thing I want to highlight is the outer shell. So we like to call this the rim shell, or the rim tire shell, and essentially what this piece is, it's merely an aesthetic piece, as we wanted to try and make this peripheral look as close to a rim as possible, while also providing functionality for the player. So although this may not accurately represent that of the rim on a tire, it is similar enough in the design where we feel like it'll get the idea across. Now, with this shell, the idea is that if you wanted to access the hardware on the inside, you would be able to remove that, and then you have access to all the hardware on the inside, so that way we as the developers and designers can be able to fix it, but anyone else can fix the hardware as well. And in order to achieve this connection, we have 10 holes allotted in the base around the entire base, and this is where we're going to be putting magnets within this base and magnets on the bottom of this shell, so that way they'll be able to connect. And instead of using some other medium like super glue or something else, that'll kind of be shooting ourselves in the foot if we were to do that, since it would be a lot harder to remove and a lot harder to access. We feel like this is a more suitable option. Additionally, on the shell, the other main thing that we've accommodated for is a small USB slot. So the way this is going to work is that this is the Arduino Nano, and that's where we're going to be receiving power. So this would be plugged into a PC, and that would be our main source of power for the entire simulation and the entire peripheral, and we've made a small USB slot to accommodate for that. So, going off this idea of removing the shell, if we were to take it off, you can see all of the hardware components on the inside. So the first thing to highlight is our essentials. We have our breadboard and our Arduino Nano. These are situated on the edge of the model rather than in the middle, and that's so we can accommodate for that USB port, so you're able to establish power, because if we were to put it in the middle, it would be a lot harder and a lot awkward to actually try and turn on the power. Now, surrounding the actual breadboard and Arduino, you'll notice this platform that we have in the middle. The reason we have this is for the rotary encoders to sit on. So instead of having the rotary encoders just kind of hanging in the air, we want them to have a sturdy foundation to go off of, and also provide more support to the tires, or to the rim, since you're going to be putting pressure on it when you're actually loosening or tightening these lug nuts. So we have 4 pillars extruding up from the base, and on that platform we have 5 rotary encoders. Now, the last piece I want to highlight that we focused on was creating these lug nuts. So these are 3/4 of an inch each, and we wanted to keep it accurate to common dimensions found on certain cars. And the car we were looking at was a 2022 Honda Civic, which has lug nuts that are 3/4 of an inch. The reason for this is because when we were conducting interviews and had the feedback, a lot of people wanted more specific tutorials for specific cars rather than general cars. So we figured we would focus on one model and replicate the steps you would need to take in order to accurately remove the yaw tire off of that car. So these lug nuts are essentially a mold that wraps around the rotary encoder as such. So as you can see in the middle, the rotary encoder would stick into the middle of this lug nut, and it would just rest on top, so that way when you actually spin the lug nut, you would be spinning the rotary encoder, and that's how we would be sending data to our simulation. Another key point that we want to highlight as well, with our design, thankfully since the interior is very hollow, we feel that wire management, we will have a lot of flexibility. So the idea is that the wires will flow from the Arduino and connect on the edges of the rotary encoders, which is why the prongs to solder the wires are hanging off the outside rather than sticking in the middle. We feel that if the wires are all congregating in this middle section here, it might be a little bit messy, so we wanted to keep a lot of areas as free as possible, but we have a lot of flexibility in terms of managing our wires and also potentially hanging them up on the sides of the shell. And that is something that we also just wanted to highlight as well in terms of the management we were planning on that end. And finally, to highlight the exploded view animation, I'll keep this playing on repeat and explain as this is playing. So you'll get a glimpse of how we envision everything connecting together. So as you can see, the lug nuts at the top will be extended out from the holes in the actual shell at the top, as you can see here. And the rotary encoders are going to be sticking through that shell, and with the mold we've created on the lug nut, they're going to be just resting on the actual dial of the rotary encoder that spins. You'll then see that the shell disconnects from the base. The base is hosting the Arduino and the breadboard, as you can see here. And aside from that, the platform in the middle is going to be you can see how that actually is going to work. So that's going to be right in the center, and it's just going to be hanging over the breadboard and the Arduino. And to clarify again, the rotary encoders will be resting on the on this platform for additional support. And that is all for the exploded view animation. Thank you for listening to our presentation.